Question number 1 is asking for the net force on a 4-kilogram ball in free fall. If we're in free fall, the only force acting on the object is the force of gravity. And the force of gravity is equal to the mass of the object times the acceleration of gravity. So, given the mass of the object, we can multiply that by 9.8, the acceleration of gravity, and find the force of gravity, and that's the only force, because we're in free fall. So that's your final answer. Number 2, Jack and Diane. They're ice skating. So if you have two people who are ice skating and they push off of each other, or it doesn't have to be ice skating, it could be any two people pushing off of each other, you're going to experience the same exact force. Remember, Newton's third law says that two opposing forces are going to be equal and opposite. And sometimes this is a little bit hard to conceptualize, because if you have a really big person and a little small person, and you're pushing off of each other, then the little tiny person is going to go flying, and the big person is not going to go very far. But that's their acceleration. They experience the same force, even though the accelerations can be drastically different. So the moral of the story is they both experience the same force here because of Newton's third law. So given we have a mass and we have a force, and the question is asking for the acceleration, we can use Newton's second law here, plugging in for the force and the mass. We can divide and find the acceleration. So this is just the acceleration of Diane, which is what the question is asking. And if we solved for the acceleration of Jack, it would certainly be different, because he has a different mass. Number 3, the question is asking for the mass of a 100 Newton shipping case. So remember, weight is the force of gravity. So the question is giving us the fact that the shipping case has a force of 100 newtons.
Jada Furry to the front office. Jada Furry to the front office.
What they're referring to there is the weight. If you say a 100 Newton shipping case, or a 60 Newton man, or a 2,000 Newton jet, what you're referring to is the mass. So they're giving us the mass, the weight. What they're referring to is the weight. They're giving us the weight, which is also the force of gravity. Weight and force of gravity are the same exact thing. So they're asking for the mass. Well, we know the acceleration because it's gravity, and we know the force of gravity, so we can plug into Newton's second law here, and we can divide and solve for our mass. The big takeaway here is that weight and the force of gravity are the same exact thing. Question number 4, we're talking about the elevator. So I want to pause here for a second and really talk about what this means. So we have our man standing on a spring scale here. And let's examine the free body diagram of the man on the scale. We have a force up, that's the normal force. We have a force down, that's the force of gravity. If you're not accelerating, then those two forces are equal. And the key concept here is that what the scale shows, what the scale reads, is the normal force. Think about it. The scale doesn't really know how much you weigh. It doesn't have a brain. It doesn't know your mass. But it knows how much it's pushing up on you. If you take a scale apart, it's got a tiny little spring inside. And the only thing that the scale knows is it knows how hard it's pushing on you to keep you up. So when you go into your bathroom and you step on your scale, you are pushing down on it with a force of your mass times 9.8. And the scale is pushing up on you. And if you're not moving, if you're not accelerating, then the force that the scale is pushing up on you is equal to your weight. So that's why it tells you how much you weigh, because your bathroom is not accelerating. If you went into your bathroom and tried to weigh yourself while your bathroom was accelerating, then it would not give you the right weight. Your weight doesn't change, but what the scale is telling you is really the normal force. It just reads the normal force that it pushes back up on you. So let's imagine two different scenarios here. We have our same guy standing on our same magenta scales here. I'm going to draw our free body diagrams. We have the normal force up and the force of gravity down in both cases. Let's imagine in the first case that we have a net acceleration in the up direction. If we have a net acceleration in the up direction, then that means that the forces are imbalanced, and the force up is going to be greater than the force down. The normal force is going to be greater than the force of gravity. And in that case, the scale reading is going to be higher than it usually is, because the normal force is greater than the force of gravity. the scale is going to tell you a weight that is not your normal weight. It's going to be greater than normal. And the opposite is true if you're accelerating in the down direction. The forces are imbalanced because we have a net acceleration. And in this case, the force of gravity is greater than the normal force because you're accelerating downwards. So the scale reading is going to be less than it usually is. In other words, you're going to feel weightless. And this is exactly what happens if you've ever been on one of those rides where it just kind of drops you, or if you've been in a roller coaster where it goes down, or even in an elevator. When it starts to go down a little bit, you feel weightless just for a little bit. And that's not because your weight is changing, but it's because the normal force is changing. And that's what the scale tells you. The scale reads you the normal force. Same is true if you're going up, you feel a little bit heavier than usual. It's not because you actually are heavier, but it's because the normal force is changing. Okay, let's look at number 4. We have the mass is given for the television. The normal force is given. Now, how do I know that the normal force is given? Well, look at the problem. It says the scale reads 78.4 newtons. And what the scale reads is the normal force. We're looking for the acceleration. So let's find the force of gravity here. We have the mass, we know the acceleration of gravity, so we can find the force of gravity, 73.5 newtons. Check out our free body diagram for a second. Force of, the normal force up, force of gravity down. Newton's second law says that force is equal to ma. The sum of the forces is equal to the mass of the whole system times the acceleration of the whole system. So what's our sum of the forces here? Well, we have the normal force in the up direction, we have gravity in the down direction. So the sum of the forces is the normal force minus the force of gravity. And we can set that equal to the mass of the whole system times the acceleration of the whole system. Let me say that one more time. We have the normal force in the up direction. We have the force of gravity in the down direction. So the net force, the sum of the forces, the total force, is the up direction minus the down direction. Normal force minus gravity. And that equals the mass times acceleration of the whole system. That's just Newton's second law right there. The mass of the system is 7.5. The acceleration is unknown. We know the normal force because that was given. We know the force of gravity. We just figured it out. So we can solve for A and get the acceleration. 0.65 meters per second squared in the up direction. I know it's in the up direction because the acceleration is positive, but also if you look at your forces, take a look over on the left there where I have my forces written down. The normal force is 78.4, and the force of gravity is 73.5. So if the normal force is greater, then it must be accelerating upwards. If the force of gravity was greater, then we would know that it is accelerating downwards. Number 5, we're given different scenarios on an elevator, and we need to figure out what the scale would say. In other words, what's the normal force? Remember, the normal force is what the scale reads. Every time you step on the scale, you're reading your normal force.
Please contact the front office.
Okay, let's stop there for a second. So the force of gravity I calculated by taking the mass, which is given, times the acceleration of gravity. So I get the force of gravity to be 520 newtons. Now the question is, for these 4 different scenarios, what is the normal force? Knowing that the force of gravity is 520. So if this was a scale in your bathroom, and your weight was 520 newtons, when you stepped on the scale, it would read 520 newtons because there is no acceleration. Okay, part A. The elevator moves up at constant speed. Constant speed means no acceleration. No acceleration means no force. So there's no net force. The forces must be balanced. If you have no acceleration, there's no net force. The forces equal out. They're totally balanced. So in this case, the normal force is just going to equal the force of gravity, which we've already discovered. So that's going to be 520 newtons. For scenario B, we have a negative acceleration. It slows down at 2 meters per second squared while moving upwards. So how do I know it's negative? You're moving upwards and slowing down. That's how I know the acceleration is negative. Sum of the forces is equal to mass times acceleration. That's Newton's second law. And again, the sum of the forces is the normal force minus the force of gravity. Mass is given. Acceleration is given in part B. Let's plug in for our sum of the forces here. Now, we don't know the normal force. That's what the question is asking. The question is asking what would the normal force be if these things were the case. So we can plug in, we know the force of gravity, we know that mass times acceleration, so we can find the normal force. So once again, the question is asking what would the scale read? the scale reads the normal force, so all we're doing here is solving for the normal force. Part C, it actually gives us the same acceleration. So how do I know that? Well, let's read it. It says it speeds up at 2 meters per second squared while moving downward. If we're moving downwards and speeding up, that's also a negative acceleration. So it's the same magnitude. So if the acceleration is the same magnitude, all your calculations are going to be the same. And the normal force is going to be the same thing. It's going to be 414 newtons. And that kind of makes sense, too. If you imagine being on that elevator, if you're moving upwards and slowing down, you feel a little bit weightless. And also, if you're in an elevator and you're speeding up in the down direction, you also feel a little bit weightless. So in both of these cases, the normal force is a little bit less than the force of gravity, giving you that weightless feeling. Finally, for part D, it moves downward at a constant speed. Again, if we're at a constant speed, that's no acceleration. And if you have no acceleration, you have no net force. If you have no net force, then the forces must be balanced. They must add up to 0. The sum of the forces is the normal force. Okay, here we go. Yeah, so the forces must be balanced. They must add up to 0. So if the force of gravity is 520, then the normal force must be also 520. Number 6, we have a guinea pig. And the question is, how much force would we need to lift it? Let's examine the guinea pig just hanging out on flat ground. He would have some force of gravity down and some normal force up. And the normal force would equal the force of gravity while he's just sitting in his cage. If he's not accelerating upwards or downwards, the two forces would cancel each other out. Let's calculate the force of gravity. We have the mass of the guinea pig handy, and we also have the acceleration, so we can calculate the force of gravity. So in order to lift the guinea pig, you must overcome that force of gravity. You must have some sort of net acceleration upwards. And in order to overcome the acceleration of gravity, you must apply a force that is greater than the value of the acceleration of gravity. So if you apply any force that is greater than 4.9 newtons, then you're going to accelerate the guinea pig upwards. You're going to have an unbalanced force, and the up direction will prevail. So any answer greater than 4.9 newtons is a valid answer to number 6. Number 7, we have a diver, and we are jumping off a cliff. The mass is given, the distance of the cliff or the tower, whatever, is given. Velocity initial, we're going to assume is 0 because it doesn't say any sort of initial velocity. Velocity final is what the first question is asking for. The acceleration, we're falling. Remember, this is a diver jumping off of a tower, so the acceleration is going to be gravity. The equation that I've chosen to use here is this one. Again, I know to use this because this has all the variables, including my unknown, in it. So we can plug in here, and we can solve for the final velocity. And you get 14 meters per second. Part B is asking for the force exerted by the water. Well, let me plug in all my new knowns here. And it's asking for the force. I don't know what the force is. Well, how do you figure out a force? You need to do the mass times the acceleration. Well, I don't know what the acceleration is either. We're not talking about gravity here. We're talking about after you hit the water, you slow down very quickly, right? We've all experienced this. If you jump into a pool of water, you're going to slow down and come to a stop. And we're looking for that acceleration because the question is, what is the force exerted by the water? So we need to find the acceleration due to the water. And we can figure that out by using our Vf squared equals Vi squared plus 2AD equation. In this case, the velocity final is going to be 0 because we're coming to a stop. The velocity initial is what we found in part A, and the distance is given. So once we find the acceleration, we can plug back into Newton's second law to find the force of the water on the swimmer. So this kind of seems like a lot of work. How did I know to do all these things? You got to work backwards. The question is asking for force. In order to get force, I must find acceleration. In order to find acceleration, I got to use my kinematics equations. And there we have it. Part A, we have a raindrop. Here's the free body diagram for the raindrop. When it's falling, the only force acting on it is the force of gravity. And we can calculate the force of gravity because we're given the mass of that raindrop. It's a very small mass. And I converted on the fly here to kilograms. Let me show you exactly how I did that. We were given milligrams. So I'm going to go milligrams to grams, so you got to move the decimal over 3 places. And then to go from grams to kilograms, you got to move the decimal another 3 places. So that's how I got 2.45 times 10 to the negative 6 kilograms. The reason why you need to use kilograms is because the units of force are newtons, which is kilograms meters per second squared. So anytime you're using force, you have to convert to kilograms. Number 9, we have 2 blocks on top of each other, and they want to know the forces between the blocks. Let's just draw a free body diagram for the 6 kilogram block first. The only force acting on it is in the down direction. Oh, that's not true. There's a force in the up direction too. I forgot to draw that. But for the purpose of this question, the only forces acting between the blocks are the force of gravity pushing down on the 7 kilogram block and the normal force of the 7 kilogram block pushing up on the 6 kilogram block. So let's calculate that force of gravity here. We have the mass given. We know the acceleration of gravity, so we can find the force of gravity on that block. So now the answers are simply 59 newtons in the up direction for part A, because it's asking for the force of the 7 on the 6. And then for part B, it's 59 newtons down, because it's asking for the force of the 6 on the 7. So this is a relatively simple system here. You really just have the force of gravity of that top block pushing down on the second one. So once you find that, then the forces between them are just going to be equal and opposite. Number 10, this is our jet plane taking off. We're given the force of gravity. How did I know that? It doesn't say anything about the force of gravity in there. Well, it gives you the weight. It says a 2.75 times 10 to the 6th Newton jet plane. That's like saying a 300-pound man. It's like saying a 100 Newton crate. It's like saying a 10 kilogram child. It's just simply giving you the weight of the object. And remember, the weight is the force of gravity. So the first thing I wrote was the force of gravity equals 2.75 times 10 to the 6th. They give you an applied force. The jet engines have an applied force of 6.35 times 10 to the 6 newtons. We don't know the distance. That's what the question's asking for. And they give us the final velocity that's required for the aircraft to take off. The velocity final is given in kilometers per hour. Eventually, you're going to need that in meters per second. I just went ahead and did it right there. The velocity initial we're going to assume is 0 because it doesn't say anything about it, but also it's an airplane taking off. So it's going to start from rest, and then it's going to speed up, and then it's going to take off. So what are we going to do here? The question is asking how much runway space do we need? Well, the first thing you want to do is you want to find the acceleration due to gravity. Let me stop here. We're getting a little bit ahead of ourselves. The first thing you want to do is you want to find the mass of the aircraft. And the way to do that is we can use the force of gravity, which we know, and we know the acceleration of gravity, 9.8. So we can do a little bit of dividing here to get the mass of the aircraft. Once we get the mass of the aircraft, we can find the acceleration of the aircraft because we know the force exerted on the aircraft. So as it's taking off, the force is that applied force, that 6.35 force. And that's equal to the mass of the aircraft times the acceleration. So we've just found the mass, and now we can find the acceleration of the aircraft. Once we get the acceleration, we can solve and find the distance of the runway using our kinematics equation. I want to make a note here that I did a decent amount of rounding. Any answer between 136 and 140 meters is fine. So, Mr. Holt, how in the world did you get here? How did you know to do that and that and that and that and that and that and that? Well, sometimes you just got to look at what you're given, take it apart a little bit, extrapolate as many variables as possible so that you have the most possible to work with. The question was asking, what is the distance of the runway? Well, if it's a distance, I need to use one of my kinematics equations. In order to use one of my kinematics equations, I'm going to need some sort of acceleration, some sort of time. If I'm given forces, I know I can find an acceleration, so that's what I did. I thought to myself, all right, I need an acceleration. Well, I have a force. Let me use my force to find my acceleration. And then once I get my acceleration, I can plug it back into my kinematics equations, and I can solve my, my problem. Number 11. We have an air hockey puck. The mass is given. The applied force is given. The time is given. The question is, what is the acceleration? Well, since we're given a force, we can find the acceleration. Force equals mass times acceleration. The force is given, the mass is given. We can divide and find the acceleration for part A. Part B is asking for the final velocity. Well, we have all of our variables to plug into this, this kinematics equation right here. Okay, have a good night.